So last time we saw how we can calculate the magnetic field created by a wire carrying current. You get these magnetic fields going around in a circle around the wire, and they get stronger the closer you get to the wire. Now, of course, you only have a constant current going through a wire sometimes. Sometimes you want to alternate the current and have it go back and forth, back and forth. I've set that up in our code. I told you to ignore this time loop previously. Now we're ready to take a look at it. What we're doing here is we're moving forward in time. We've set up a rate of 100 frames per second here. And what I can do is I can make the current a function of time. So here what I've got is a change in the magnitude of the current. So we're going to be adjusting this like the cosine of time. We've got a period defined up here to be this would be 1 second in real life. The computer may or may not render it as an actual 1 second depending on our frame rate. But basically here for all of the sources, for every element of current in the sources, we're going to update its current value to be the new current value. So we were to talk about the current value and the new current value. Think of that as the magnitude of the current because we still have to have a direction associated with it. So we're going to have to update that current arrow's axis to be the source's axis times that source's current. So that way we get a change in the visual for the arrow. But just by changing this magnitude here, we are able to keep the magnetic field vectors updated down here because we're just referencing the current here and then we have the axis here. So by the time it flips around to the negative direction, this value just becomes a negative. We don't actually have to change the axis of the cylinder, which is good because otherwise the cylinder would be growing and shrinking and that would be weird. So let's hit Control 2, see what difference this makes now that we no longer have a constant current. So first let's make sure that what is changing is what we think is changing. The cylinder itself is remaining stationary, right? So your wire doesn't really move when you're running a circuit. Hopefully it does, and if not, you might want to unplug the circuit. But you've got the current arrow oscillating back and forth like a cosine, going between one extreme to another. And look what's happening to our magnetic field vectors. They are oscillating back and forth, but they always obey the right-hand rule. So when the arrow points into the page, they're going clockwise. When the arrow points out of the page, they're going counterclockwise. And this gives you an idea of why they want you to turn off your electronics on an airplane, is because you have all of these magnetic fields oscillating back and forth. Not exactly a random variable that you want to be throwing in on an airplane during flight. Now, of course, last time we also set up having more than one wire of current. So let's uncomment another wire here. So we'll have one going into the page, one going out of the page. We got a pretty cool pattern there. Let's see what that looks like animated. Oh, I have these magnetic fields too close to that. Let's get rid of that set of observations. Yeah, let's delete this one here. Let's not delete it. Let's just comment it out. There you go. Never delete anything. Always just comment it out. You never know when you might need it again. Cool, so here we've got two wires going what we call anti-parallel to each other. So the wires themselves are quote-unquote parallel, but their currents are anti-parallel since one's going always going the opposite direction of the other. And you see what happens to our magnetic field here. We've got them oscillating. It's basically reducing in size and then kind of going into the mirror image of itself, kind of like what we saw when you flip a positive charge with a negative charge for electric fields. Now, of course, I commented last time that this is kind of an artificial case because you rarely have current just going to nowhere, right? These electrons have to go somewhere. So what we're now going to add is a wire of current connecting these two ends here and another wire of current connecting these two ends here, and we'll do it in such a way that the current goes around the loop. But before we do that, let's turn off the animation. Let's just comment this out. And that way we can just observe the static case and then we'll come back to the dynamic case. So here I've got another two wires of current. So I'm going to have 4 cylinders total. The way I've set up their positions and their axes enables them to connect to each other around in a square. Let's double check, make sure that that's what happens. So let's ignore the magnetic field for right now. If I look just at this square of current, I can see that if I'm an electron here, I follow the current along this way, I end up in this corridor here, and then I come down this corridor, I come down this corridor, and then I continue to go around this way. By the way, I use the word corridor. I used to think that the Hall effect was called the Hall effect because it happened in a hall of current moving down. I didn't know it was named after somebody named Hall, so my apologies to Dr. Hall there. The fact that these cylinders don't quite meet up here doesn't really matter. We're not actually moving the electrons from one to the other like I did in a previous video about circuits. I wanted to be easy on myself there. So we have a loop of current going around here. And what we get is this interesting pattern. We've got the magnetic field lines kind of going around in a circle like this, kind of like when you have an electric dipole. And in fact, this is what we would call a magnetic dipole. The way you can envision any sort of natural magnetic dipole that occurs like in an atom is by current going around, because we know that in an atom we have electrons running around the nucleus as well as spinning on their axes. And so that's what produces a magnetic field in quote-unquote magnetic materials, is by having these tiny microscopic currents kind of all lining up together. So this gives you an idea of what the magnetic field of a magnetic dipole looks like, which is pretty cool. And now we should probably take a look at the main event for this video, which is getting these things to oscillate with time. So let's turn our current oscillator back on. So I'll uncomment this. So all of these currents are now going to oscillate like the cosine of time. Let's hit Control 2. So if you look at the current, you've got the current going clockwise and counterclockwise, clockwise and counterclockwise, and you have your magnetic field oscillating accordingly. So notice the vectors, they're always pointing in the same direction, right? You're never going to get this one to point off this way. You're never going to get this one to point left or right, but their direction is, their magnitude is adjusting, and then their direction is shifting. So they're going like a cosine. And again, as before, the farther away you get, the weaker the magnetic field becomes. In fact, what we'll take a look at next time is we'll ignore all the stuff going on around the edges. We'll take a look at these magnitudes along here going away from the center of the ring, and we'll see how the magnetic field magnitude dies off as we get farther away from the loop of current. So thank you so much for watching. I will see you next time. Bye-bye.